Hello, everybody. Welcome back to class. Feel free to say hi if you're in the chat. See, there's a few of us here so far. Got about a minute or two before class actually starts. Looks like my brother is in the chat. First one to say good morning. Taylor, Emma, good morning. Cal, good morning. Good morning, Shutong. All right, well, it's 9 o'clock, and we won't forget like we did yesterday. So if anybody wants to join in on the April Fool's Day edition of the simultaneous SIP, you do so now. Feel free to type in the word SIP in the chat if you joined in. Or if you didn't join in. Okay, so we're going to finish up section 5.3 today. We just had this last example. And then we'll move on to 5.4. Okay, and we're doing pretty good in terms of our pace. We should be able to finish through 5.5 by Friday. And hopefully we'll have like half a class of review on Friday, but we'll have to figure it out. So, okay, diagonalize A if possible. Emma's sister, I'm glad you joined us for the simultaneous SIP. So there are two sibling pairs joining in the simultaneous SIP, Emma and her sister, and then me and my brother, I guess. I'm not sure why he comes to these things, but that's where we're at right now during this isolation time. Okay, so we want to diagonalize A if possible. So we start by finding the eigenvalues. We find the eigenvalues. Here we have a triangular matrix, right? It's not upper triangular. It's lower triangular, but still everything above the main diagonal is 0. So it's really easy to find the eigenvalues. They're just the entries on the main diagonal. So the eigenvalues are 5 and -3. So now what we want to do is just find bases for the eigenspaces corresponding to each of those eigenvalues. And then we're basically done with the question. So we'll start with lambda equals 5. So for lambda equals 5, basically what we want to do is find the null space. So this. Right, and I'm not going to go through all the steps here, but so find the matrix A minus 5 lambda, which is subtract 5 off from the main diagonal, and then just put it into reduced row echelon form and solve. Our basis is -8, 4, 1, 0. And -16, 4, 0, 1. Okay, so check this on your own. But again, we've done a lot of examples like this, so I don't want to spend too much time. So there's two basis elements here when lambda equals 5. We'll do the same thing when lambda equals -3. And we get the vectors v3. So again, you'd find the null space of a minus -3 lambda and find a basis for it. And so now we want to count. Do we have 4 total eigenvectors? And we do, right? Each of these, the dimension of the eigenspace for lambda equals 5 is 2. The dimension of the eigenspace for lambda equals -3 is 2. 2 plus 2 is 4, which is the number of columns, rows and columns of our matrix. So we can diagonalize A. So A is diagonalizable. Which means we could write A as P, D, P inverse, where P is the matrix formed by whose columns are the eigenvectors. And D is the diagonal matrix whose entries along the main diagonal are just the eigenvalues. So the first two would correspond to lambda equals 5. The next ones would be lambda equals -3. So if you have any questions, type them in now, because there's a little bit of a delay. But if you went through and found the inverse of this matrix, and then did the matrix multiplication, P, D times P inverse, you should end up with the matrix A. So I'll give a couple seconds for you to write this down, but yeah, so I skipped a lot of steps here, but you should go through and figure out, why are V1 and V2 a basis of the eigenspaces, and why is V3 and V4 a basis for this eigenspace? Okay, well, if there's no questions, we're going to move on to the next section. If you have a question still, feel free to just type it in. So this is section 5.4. Eigenvectors and linear transformations. Okay, so these are both. So we've talked about eigenvectors, for the last few classes, and linear transformations. That's something we talked about, I guess, before the COVID-19 took us down. Way before that, actually, like a month ago or so, we talked about linear transformations. So we'll kind of review what a linear transformation was, and we'll see how they're related. So recall that any linear transformation T from Rn to Rm can be expressed as T of x equals AX. Where A is called something. Does anybody remember what we called this matrix A for linear when we were dealing with linear transformations? I'm sure it's somewhere in your notes, but I'll write it out now. So A was called the standard matrix of T. Yeah, Taylor, exactly. A was the standard matrix. Okay, so but this is for linear transformations between Rn and Rm. We're going to define, or we're going to express linear transformations going from some general vector space, maybe polynomials, to another vector space. So that's the idea of this section. So instead of having Rn to Rm, we'll just have some general n-dimensional vector space to some general m-dimensional vector space. So we will now consider linear transformations between two finite dimensional vector spaces. Okay, so we don't have to go from Rn to Rm. We're going to be going from, let's say, V to W. So we'll let. So what we're going to do now, before we get to looking at some examples, we're going to kind of do a little bit of the build-up to why what we're going to say is true. So we're going to kind of prove. We're not going to actually prove, but we're going to go through the logic behind the big theorem in this section. So let V be an n-dimensional vector space. And W be an m-dimensional vector space. And T be a linear transformation from V to W. And we'll sketch out a picture in a second. But yeah, so we have an n-dimensional vector space. So this is taking the place of Rn. We have an m-dimensional vector space. This will take the place of Rm. And T maps V to W. Right, again, and just if you want to picture something mentally, maybe these could be polynomials. So Pn minus 1 and Pm minus 1, if you wanted to think about them not in terms of column vectors. Okay, so what we're going to do is choose bases B and C for each of these vector spaces. Okay, so B is some basis for V, C is some basis for W. We'll take some vector X in V. The B coordinate vector of X is in Rn. And the C coordinate vector of T of X is in Rm. Okay, so we haven't really done anything yet. This is all just build up. Okay, so let's draw a picture of what we have, and then I'll answer any questions before we get to the actual math. Okay, so let's say that this here is V, over here is W. And we have some vector in V, which we call X. And it gets mapped by T to some vector T of X. But we could also map X let's say this is Rn down here. We could also map X to its B coordinate vectors in Rn. Similarly, we could map T of X to its C coordinate vectors. What we want to find is the matrix that maps this point in Rn to this point in Rm. Okay, so just to write that down, we want to find the matrix, which we'll call M, that maps the B coordinates of X to the C coordinates of T of X. So i.e., we want to find the matrix M such that the C coordinates of T of X is equal to M times the B coordinates of X. Okay, so just to kind of recap, and please ask any questions because I know this is a very theoretical. What we're doing here seems very theoretical, but basically we're experts. At least I hope we're experts at dealing with linear transformations from Rn to Rm. Right? We just found the standard matrix, and then it was like, business as usual. Once we found a standard matrix, it was really easy to work with. Here we want to have the equivalent of a standard matrix. We want the equivalent of a standard matrix when we're dealing with just two abstract vector spaces, V and W. And so we're not really sure how to do that, but we do know how to treat a vector in V as a point in Rn, right? Those are the B coordinate vectors. And similarly, we know how to treat a vector in W as a point in Rm. That's the C coordinate vectors. So now we just want to find the matrix that maps this vector over to this vector. Any bit of feedback would be really appreciated. We could have a question mark face or a thumbs up face. Yeah. No feedback means I'm just going to keep going. So what we're going to do now is we're going to just try to figure out how do we find this matrix M. Let's do an example. We will, Emma, and once we figure out how to find M, we'll do plenty of examples. Alex gives a big smiley face and Taylor says thumbs up. Good, yeah, but Emma, we'll get to an example in a second. Let's just first figure out how to get M. Okay. So X lives in V, and we said that B is a basis for V. So we could write X as a linear combination of the basis elements of V, right? That's what it means to be a basis. There's a unique way to write every element in here as a linear combination of the basis elements. So we'll say X equals R1, B1 plus Rn, Bn. Right, so if X can be written in this way as a linear combination of the basis elements of B, another way to write that, so this is equivalent, is saying that the B coordinates of X is the vector R1 through Rn. Right, these are exactly the same thing. This is saying X is written as this linear combination of the vectors B. Another way to write that is, the B coordinates of X is just R1 through Rn. So if we evaluate our linear transformation to X, that's evaluating the linear transformation to this right-hand side. Which I claim, and now in the comments, tell me why this is true. We could rewrite this as R1 T of B1 plus ... plus Rn T of Bn. So why are we allowed to take T of this linear combination and express it as a linear combination of T evaluated to each of the basis vectors? What property are we using? That's one of the properties of a linear transformation. Exactly, yes. We're using the fact that T is a linear transformation here to allow us to break it up like this. And now let's look at what the C coordinates of T of X are. So let's take the C coordinates of both sides. And taking the C coordinates is also a linear map. So we could just evaluate the C coordinates of each of the vectors here. Okay, so we have the C coordinates of T of X is equal to this linear combination. Well, we could rewrite this part, the right-hand side, as a matrix times a vector. Okay, so what we have here is the c coordinates of t of x is equal to this matrix here times the vector r1 through rn. Well, that vector is the b coordinates of x. So we just expressed the c coordinates of t of x as a matrix, which we'll call M. We just expressed the c coordinates of t of x as a matrix times the b coordinates of x, which is exactly what we were hoping to do. Okay, that's exactly what our goal was. So this matrix M, whose columns are the c coordinates of the image of the basis elements under T, is our change of basis, or is our standard matrix for this transformation. So let's write this down as a definition, and then Emma will get to an example. Okay, so this matrix M is it's a long name, matrix for T relative to the bases B and C. Okay, that's a long name, but we can just connect all these lines. Okay, and the way we get M, it's a matrix whose columns are the c coordinates of the images of the basis vectors. Okay, so this, I know we did a lot of build up to this, but I kind of wanted to give you a sketch of why this is true. So if we, basically what this is saying is, the way you get the c coordinate vector for t of x is you find this matrix M and multiply it to the b coordinates of x. Let's look at an example. But if there's any questions, please ask them in the comments. Okay, so suppose B is the basis B1, B2. Is a basis for V. So we don't know what this vector space is. We just know it's a vector space. And C, which has 3 elements, is a basis for W. Okay, so we have a 2-dimensional vector space and we have a 3-dimensional vector space. We'll have T, which maps V to W, be a linear transformation. Such that T of B1 is equal to 3C1 minus 2C2 plus 5C3. And T of B2 is equal to 4C1 plus 7C2 minus C3. And the question is find M. M being the matrix for T relative to B and C. I just don't have space to write that. Okay, so does somebody want to guess in the chat or explain in the chat how you're going to go about finding M here? Yeah, Liza, that's exactly right. So we need to get the C coordinates for the image of B1 and the image of B2. But we could just read those off as the coefficient. They're just the coefficients here. I'm kind of sad that I erased that because that was probably I should go back and take a screenshot of what the board looked like before I erase this, because this is some of the most complicated drawings we've had all semester. And we did it from my apartment during the isolation. Okay, yeah, that's exactly it. So just note that the C coordinates of the image of B1 is the vector 3, -2, 5. And the C coordinates of B2 is the vector 4, 7, -1. And so we're done. M, the columns of M are just these vectors, right? That's what the definition says. Okay, in this map, if we just took some general element of V and multiplied it by this, and multiplied its B coordinate vectors by M, it would give us the C coordinate vectors of its image under the transformation by T. Okay, so we're going to look at a special case when we're mapping from V to V, right? So we're going to have the same vector field in both the domain and the codomain, and both B and C will be the same basis. So when W equals V and C equals B, so we have the same vector space and the same basis, we call M the B matrix for T. And we write bracket T sub B. Okay, so T here is the linear transformation. So if we're mapping, and we'll do an example right now. If we're mapping some vector space to itself, and we keep the same bases, then a lot of this notation is not necessary, so we could just write it as TB. Okay, so let's look at an example. Okay. So the mapping T from P2 to P2 defined by T of A0 plus A1T plus A2T squared is equal to A1 plus 2A2T is a linear map. All right, now here's my question for you. This map has a name, and I guarantee you've seen this map before. So does anybody know what this map is that we're dealing with here? It's not something from this class, but it's something you've seen in a different math class. Okay, so we have some map that takes a polynomial and sends it to a different polynomial. So the question is, find the B matrix for T if B is the standard basis. Yeah, Alex, correct. This is the derivative, right? The map, the derivative map is a linear map. Yeah, so the question is, find the B matrix for T. So basically what we want to do is figure out what does 1 get sent to, what does T get sent to, and what does T squared get sent to. So yeah, we want to figure out what does each of the basis elements get sent to, and then try to express this as a matrix. So I'll give, I don't know, let's say 2 minutes. I'm going to try to, there seems to be a little bit of a glare, so I'm going to try to work on that glare while you guys try to work this out. That may have made it worse. All right, whatever. It's better, I guess. Okay, did anybody have any luck with this? It's okay to say no. I just kind of want a little bit of feedback so I could see. It's just so hard to right, during class I'd walk around and get a sense if people were following or not. With the internet thing, it's definitely the big challenge. Okay, well, if you were able to get something, great. If not, let me kind of explain how we're going to do this. We want to just evaluate the map, find the image of each of the basis elements under this map. Okay, so we'll start with t of 1. So that'd be t of 1 plus 0a1 plus 0a2 t squared, which is 0. And the b coordinates of 0 is the vector 0, 0, 0. Okay. The next basis element is t. So that's 0 plus 1t plus 0t squared, which is 1. The b coordinates of 1 is just the vector 1, 0, 0. And then last we look at t squared. And our map says, so we're sending 0 plus 0t plus 1t squared should be sent to 0 plus 2t. And the b coordinates of 2t. What's the b coordinates of 2t? So somebody answer that. So we'll have some answer here, and then we can put this all together. T sub b is equal to, these are just the columns of our matrix. Okay, well, I'll fill in the blanks. It's just read off the coefficients. There's a 0 for the constant term. There's a 2 for the t term. Yes, Cal is exactly right. 0, 2, 0. Right, there's no constant term. There's a 2 for the linear term, and there's no degree 2 term. Okay, so if you multiply this matrix to the coordinate vector of some polynomial, of some degree 2 polynomial, what you're doing is taking its derivative, which I think is pretty neat. Okay, let's state a theorem and see if we get to an example. And feel free to ask questions. Oh, can you explain how you got 0, 1, 2t again? Yeah, okay. Good. So 1 is really the polynomial 1 plus 0t plus 0t squared. Okay, so our map looks for the coefficient of t, that's our new constant term, and then it looks for the coefficient of t squared, and 2 times that is our new linear term. Okay, so if you took the polynomial, just for clarity, maybe we could write it like t of 1 plus 0t plus 0t squared. Our map says, give me the coefficient of the linear term plus 2 times the coefficient of the squared term times t. And then we would do the same thing here, but instead of having 1 plus 0t plus 0t squared, this is 0 plus 1t plus 0t squared. And so it's just looking for the coefficient of the linear term, which is the coefficient of t, which is 1 here. And then same thing down here. Did that answer your question? Okay, so let's write this theorem, and then we'll write down an example, but we won't be able to finish it. Right? We have not even mentioned, this section was called Eigenvectors and Linear Transformations. We have not talked about eigenvectors yet. So we'll get to that now. Okay, so suppose A is diagonalizable. Okay, so A is equal to P d P inverse. So the theorem says if B is a basis for Rn, okay, A is an n by n matrix. If B is a basis for Rn, formed by the columns of P, okay, so P is a matrix. We get a basis formed by its columns. Then D, so the theorem says then D is the B matrix for the transformation which sends X to AX. Okay, and so let's look at an example, or let's write down an example that I would like you to try tonight. We'll start class with it tomorrow. That is an application of this theorem. Right, so this theorem says if we have A is just some diagonalizable matrix, and B is a basis formed by the columns of P. Remember, P was formed by the eigenvectors. That's where the eigenvectors come in. Then to get the B matrix, we just look for the diagonal matrix that contains all the eigenvalues. That's what this theorem is saying. So, so here's an example. To find T from R2 to R2 by T of X equals 7, 2, negative 4, 1 times X. And then find a basis B such that T of B is diagonal. Okay, and then notice that this matrix here, we've done examples with computing the eigenvalues and the eigenvectors. So look back in your notes for some, if you want to check your answers about finding the eigenvalues and eigenvectors. But we're going to use this theorem here. Basically, we want to make our basis, we find B such that, so we want to find, let's diagonalize A and then use the columns of P will be the basis B. Okay? Whoa, this is like the first time I'm taking you all the way to the end of class. Okay, that's all I have for today. Tomorrow we'll pick up with this. I have office hours today at 1 on Zoom, so please stop by if you have questions. If that time doesn't work, I literally do nothing all the time. So just email me and we can find a different time. Remember to hit the like button. Sorry, remember to smash the like button before you leave. It's going to help us. It's going to help us with our goal to reach 1,000 subscribers. But I'll hang out and answer some questions. But if not, you're good to go. James says, I'll check out the office hours. You have to have a Wake Forest email address to get into the office hours. See you all tomorrow.